So, hello everyone, my name is Adrien Hirvoas. I'm currently research engineer at France Energy Marine in applied mathematics. And so the topic of my talk today is the use of machine learning approaches for the analysis of floating offshore wind turbine. So, as presented by Romain during the introduction, within the DIONYSOS project, we have developed a software platform with different components. And today, my talk will be on, so you can switch, Romain, maybe to the. Today, my talk will be on the use and the development of mathematical approaches to obtain information from the physical asset and also the data obtained through numerical simulation. And so during the project of Dionysos, we have developed several machine learning algorithms, but the two families of algorithms that we have developed was the classification, where we try to detect anomalies within the data, and regression machine learning approaches, where we will try to predict some behavior of the system. So to use this kind of approaches, we need data. And during the DIONYSOS project, we had access to several sources of data. So as presented by Cesar, thanks to our collaboration, we have deployed the neuron system nodes on the towers, which is in fact a three-axial accelerometers along the tower. We had also developed several algorithms to extract data on the location of interest. And we obtain, in fact, several information of the environmental conditions thanks to numerical weather prediction models. And as presented by Cesar and Jérôme, we have also developed during the project a numerical representation of the physical asset. So we had used, in fact, the OpenFast software, which allows us, in fact, to obtain synthetic data, synthetic prediction of the behavior of the system at different locations of interest. So we had access to several sources of data. So we had different strategies during the DIONYSOS project, but the two families was classification and regression. I won't go to the details of all the methodologies that we have developed during the project. I will only focus on two approaches. One is a detection of anomaly. So the idea is to use deep learning approaches based on autoencoder to detect anomalies in the data. So it's a paper that we are currently publishing in a scientific paper. And the second aspect is continuous monitoring. So in fact, we will try to replace the costly numerical model of OpenFast, which is time consuming, by a mathematical simplification. And the main idea was to use the work of Noura Adrien, which allows us, in fact, to take into account the uncertainties linked to the replacement of the costly model by a deep learning approach. Okay, so for the first approach, the classification, I would like to first introduce the idea of anomaly. So hereafter, we see the anomaly has an observation which can be seen significantly outside from a normal behavior. But we have to find what is a normal behavior. So we can see the problem has a statistic problem where we would try to find a probability density function of a quantity of interest and try to find the distribution and the value of the distribution upon which the quantity of interest can be seen as an anomaly. So we can have two ideas, a supervised classification. So we will use the numerical model to perform synthetic anomalies of the system, and we will then learn the machine learning algorithm to detect these anomalies based on the labeled anomalies. And we can have also a non-supervised classification where we'll try, in fact, to automatically find the patterns of normal data. And this is the second aspect that I will show you in this presentation. So the idea is to, in fact, use the in situ data, so the data obtained through the accelerometers, to detect the anomalies. in fact, we will use the autoencoder. So the autoencoder is a deep learning approach that, in fact, try to reconstruct the input that is given as an input. So it uses two functions, an encoder. So it's a mathematical formulation that will extract the most important information in the input and reduce in the information in the latent space with a few dimension state. And then we have a decoder function that will extract the information from the latent space and reconstruct the input in a best way. So the idea here will be to learn the autoencoder to reconstruct normal acceleration of the system. Okay. So we need to identify the normal behavior of the system. So the idea of our approach, due to the limitation of access of in-situ data, was to identify operating and non-operating period of the system based on the accelerations. So we had to identify the two areas, two regions of operating and non-operating period. So we had access of 1 month of SCADA, and by using this in-situ data of SCADA, we were able to identify these two regimes of the system. And if we look at each period of the system, we can have access. So Romain, you can switch to. We can have access to the 18 accelerations obtained along the tower. And we will look at the spectral representation of this acceleration. And this spectral representation of the acceleration will be the input of our autoencoder. So to train our autoencoder, so our deep learning model, we had to efficiently stratify our input space. So we perform a stratification of our database based on the input weather space. So as we can see on the left side of the presentation, and based on after the reconstruction error of our deep learning approach, we can in fact identify a threshold upon which the acceleration given as input of our autoencoder can be considered as acceleration from non-operating period of the system. And so we test our deep learning approach on a test base, and we have compared the result of our convolutional artificial neural network with a kurtosis procedure used by Cercel. And we see that in fact, we identify non-operating period and operating period based on the acceleration, and that the result obtained through our deep learning architecture was better than the engineering procedure used by Cercel. Okay. So the second aspect was a regression problem. So in fact, we are using synthetic data, so data obtained thanks to the numerical model. And the objective of this second aspect was to replace the costly numerical model by a mathematical formulation, which is much more fast to run. And the idea in our study was to consider the model as probabilistic. So in fact, we will have a probability distribution as a prediction. So the idea of our work was to, Romain, maybe you can switch, was to find a formulation that will link, in fact, the weather input, so the different wind direction, wind speed, and wave direction, for example, to the acceleration. So the acceleration obtained through our numerical model in the spectral domain. So to take into account the aspect of a probabilistic point of view, we had decided to use a deep learning architecture. So we used a feed-forward neural network coupled with a transposed 2D convolutional network. But the main idea was to use a dropout. So Roma, you can switch maybe. Roma, you can switch to, yeah, thank you. So dropout is a regularization way of neural network, but it can be also used as a Bayesian perspective, and it allows us to take into account of, in fact, the uncertainties related to the replacement of the numerical model by mathematical formulation. Okay. So as I said, we are using synthetic data, so we need to perform several numerical simulation thanks to our OpenFast model. So to perform this simulation, we used the high performance computing architecture of Janzé, which is one of the most important high performance computer in France. So the next slide. So for the training of our deep learning architecture, we had to consider several input from the weather at the location of interest. So we decided to use an incast database of several years, and we had 7 variables of interest related to the weather solicitation in Norway. And so, as you can imagine, we have several combination of environmental solicitation, and we had to reduce the input space. So we performed a stratification and a selection of a combination of environmental solicitation to perform the numerical simulations. So by using this stratification, we were able to run more than 36,000 of simulation, and due to the high performance computing architecture of Janzé, we were able to run 10,000 simulation in parallel. Once our database is built, we had 2 phases to first train our numerical deep learning architecture. So the idea here will, in fact, to learn the deep learning neural network to know the relationship between the input space, the weather input space, and the related spectral representation of the accelerations. Based on the training phase, we can then have a weighted deep learning architecture, and then we can test our deep learning architecture based on a second subset, which is a test set that the deep learning architecture doesn't know during the training phase. And here you can see the response of our deep learning architecture, which allows us, in fact, to predict the acceleration in the spectral domain of one node of the S-morpho sensor architecture in one direction. And the interest of our deep learning architecture is to have one prediction and the related uncertainty of the prediction along the frequency band of interest. Okay, so as a takeaway messages, so deep learning methods and machine learning methods can be easily implemented for floating offshore wind turbine. Thanks to these methods, we can find patterns in data for classification, but also prediction. And the second aspect is at the opposite of numerical models such as OpenFast. They are really fast to evaluate, and we can use these deep learning architectures for real-time application. But the main challenge we have is to have access to data, but we can mitigate this issue thanks to the use of synthetic data obtained through the numerical model. We still have future work, so we add a limited access to sensors on the physical asset. So we want to explore the use of new sensors, and we also want to use these new sensors to detect new anomalies, because we only had access to the acceleration on the tower, but we hope that the new collaboration with FOWT will allow us to find a new pattern in the data from the different sensors that we are currently investigating. And we also want to see if we can have more complex architectures to find new information in the data thanks to the deep learning procedure. So thank you for your attention.